This is where we left off, and we were talking about my other option for elimination. And we said the eliminations can take place using P double bond O with Cl3s. So this P double bond O Cl3 phosphorus oxychloride can go through an elimination process with an alcohol and do the same thing that sulfuric acid and heat does. It rips the OH off, it rips a neighbor hydrogen off, and a double bond forms in between. Well, there's something else that we need to say too with the eliminations. And here we go. Let's take CH3, CH2, carbon, and then CH3, CH3, and OH. And let's react this with tosyl chloride, TSCl, and pyridine. What? Wait a minute. That sounds familiar, doesn't it? It should. Because we just discussed this when we started talking about the substitution section of the alcohol reactions. You know, tosyl chlorides came on to make these tosyl esters in a way that was able to get removed with a leaving group or an incoming nucleophile. Well, the same thing's going to happen here. Just bear with me for a minute. What we talked about before is, okay, well, I've got this group, CH3, CH2, carbon, CH3, CH3, and this OH. And if you remember, I hope, this tosyl chloride will come in and off goes the H, and my tosyl group goes on instead. Remember, that was the ring with the methyl group on it, the sulfurs on it. Huge big thing. That's why we don't write it. It's just too much energy for us. We're a little lazy. Well, this formed a rot, remember? ROT, the R for random alkyl group, and that's what you see to the left, the O for oxygen, and the T for tosylate. So there is the rot. Now at this point, we said that this was a very good leaving group. So if we brought in something like C triple bond N, we could promote a substitution reaction to happen. So the C triple bond N will come in, and pink, off goes the OTS, and that C triple bond N would take its place. That's kind of what we discussed, many lecture videos ago, it seems like. So these sulfonate esters have good leaving groups. Now, dehydration means removal. And we can get a dehydration to happen here. And how we do it is we use a very strong nucleophile, something that's at the very top of that list maybe, or toward the top of that list. And that one could be something like methoxide. And this will promote an E2 reaction from happening, or to happen. So an E2 reaction can happen, and it's going to convert that alcohol that we started with to a sulfonate ester, like we have ended up with right here. And that sulfonate ester, we can add a really strong base to it. And that strong base is something typically that's very small, something that carries a full-blown negative charge, and that strong base will help carry out the elimination reaction, which means my product, okay, CH3, CH2, carbon, CH3, CH3, here is the OTS, that methoxide, strong base, good leaving group, ping, off it goes. And then this carbon's going to look for a neighbor to take care of it. Which one's the best choice out of the two options that it has, because these are twins. And it's going to be more inward. It's going to be this neighbor. And when it takes that hydrogen off, that's where that double bond is going to form. There we go. It's still an elimination. It's another way that we can promote an elimination. This reaction works really well with secondary and tertiary alcohols. It doesn't react with primary alcohols that well. And that's because those primaries prefer substitution reactions over eliminations. So secondary, tertiary is fair game if this is another route for an elimination that you want to do. The problem is that this is also dabbling a little bit into what we've talked about before with substitution. This is a very good leaving group. This can, ding, off it goes, and we can replace it with something else, and that is substitution by definition. But under the right circumstances, secondary, tertiaries, under the right circumstances of a really, really strong small base, we can get an elimination to form as well. So let's look at another example problem. What alcohol would you treat with phosphorus, oxychloride, and pyridine to form each of the following alkenes? All right, so they don't want me to worry about the tosyl stuff. That's great. That was just kind of like a side note type of thing. So they want me to take a look at A, B, C, D. These are the products that we want to end up with. So these are all alkenes for that reason. And they want to know what alcohol would you use in order to ensure that this is what you get. Okay. So the criteria is that we are going to be adding POCl3 and pyridine in each case. And we want to make, in part A, CH3, CH2, carbon, CH3, double bond, CH2. That's where we want to end up. Where do we start? All right, well, we know that an elimination reaction happened. So before the elimination reaction happened, we know that this double bond was not there. We also know that the POCl3 did not allow rearrangement to take place. So I only have two choices here, and that's either that carbon or that carbon. That's it. There's no more. So now I've got to figure out where the hydrogen went and where the OH group went. What are my best choices in order for this to take place? Well, let's say that my OH was here and my H was here. If that was the alcohol that I picked, would I get the product that they told me that I needed? What do you think? Maybe not. Why? Well, this OH group would be eliminated. This carbon would look at the neighbors, the buddies, and said, which one would get me out of bail? And this carbon would have the affinity to go to the left because it's more inward. That is not what my product is wanting. That's not what question A wants. That's not my end result. I need to make sure that my double bond happens over here, not here to the left. And if this is where I put my OH group, that is what will go on because that is the preferred double bond location. So what that means is that I'm going to have to break that double bond. That's the product that I'm after. And my OH group would probably have to go here on the end with my hydrogen here instead. This will ensure that the OH is going to leave. It will not move. It's only one other choice. That's it. That other choice is the carbon to the left. It removes that hydrogen and a double bond will form at that location. And that is where we need it to go. So folks, there you go. That's going to be the answer for part A. That is the alcohol that we need in order for this reaction to work. Let's name this alcohol 1, 2, 3, and 4 carbons in total. So this is a butanol, OL for alcohol. This is going to be carbon 1 because that's where my OH group is at. It's closer to that side, so 1-butanol. And then on carbon number 2, I have a methyl group. So 2-methyl, 1-butanol. Now let's take a look at B. If I take a look at B, this is what I want to end up with. So what kind of alcohol would give me that product in an elimination? All right, well, if I use POCl3, that means those 2 carbons in the double bond are the 2 carbons that's going to be doing something for me. No rearrangement takes place. So what I need to do is erase that double bond, and 2 sites of attachment will open up. Where do I put the OH group? Is there a difference? Is there a preferred choice? And the answer is yes. If I put the OH group down here, this carbon would look at the carbon to the left and the carbon up above, and it would say, which one is going to give me a better, more stable alkene? The same thing's going to happen up here at the top. If I put the OH group that's here, which one's going to give me a more stable alkene? The one to the left or the one to the right? Well, here's the deal. If this was the case, if OH was right there, it doesn't really matter, does it? This carbon and that carbon is the same. I could put my double bond here, or I could put my double bond here, which is where it's listed, and that would be the preferred method. So there's the correct alcohol that I would need in order for that reaction to work. If you did the other carbon and you put that OH on this end and said that was my alcohol that I needed, the problem here is that sometimes that double bond would form there. You don't want it there. You want to make sure that it's getting close to this CH3 group because that's what the problem wanted. So the proper alcohol is going to be that one. Let's look at C. For part C, I'm going to have a CH3, a CH, a double bond, a CH, a CH2, and a CH3. This is what I want to make. So that means we've got to figure out an alcohol that would give me that when I begin to eliminate it. So POCl3 and pyridine. So here at the double bond, I'm going to have to erase that double bond. 2 sides of attachment here and here. And I'm going to have to figure out where is the best spot for the OH group. That's what this question wants. Do I put it to the left or do I put it to the right-hand side? Well, if I put it to the left, there is an option when this gets eliminated for this carbon to get the bail money out from the friend on the left, or it could get the bail money out from the friend on the right. Now, that's going to be the preferred way, and that's actually exactly where I want that double bond to be. Is the other carbon any better choice? Well, let's take a look. If my OH group was here, that carbon would be targeted. That would eliminate the OH group, and the neighbor buddy would bail them out. Do I go left-handed and form the double bond there? Or do I go right-handed and form the double bond there? Well, the nice thing about that option is that it really doesn't matter. It doesn't really matter which one, because this part of the molecule is the same as that part of the molecule. Look at that. It's very symmetrical there. I'm going to end up getting the same double bond no matter which way I go with this. So this is going to be a better option for me. Yes, the first way that we did it, putting the OH on the left, would work, but it would only work for some of the time. Here I have an OH group that works all of the time at this particular position. So that's going to be the better alcohol in order to choose from. If I wanted to name this, that is a 1, 2, 3, 4, 5 carbon chain. So this is a pentanol. And no matter which way that I number it, it's going to get a number of a 3. So 3-pentanol would be the best alcohol to choose from. If I wanted to name this structure here, this is a cyclohexane. So this is a cyclohexanol. This is a 1-cyclohexanol. And on 1, I also have a methyl group. So 1-methyl, 1-cyclohexanol. And 1s are understood to be there if we don't write them. So I could simply write methyl cyclohexanol instead. And it works. Finally, let's look at part D. Part D tells me that I'm going to have a ring structure. And this ring structure better have a double bond CH2 that's right there. So I want to know what kind of alcohol can I use in order to get to that point if I use phosphorus trichloride and pyridine. Keep in mind, this does not shift. POCl3, that's the good thing. That's what we've always said. So if I want to know what kind of alcohol would be used, that's the best choice. There's my double bond. Bing! There we go. Erase it. 2 sites of attachment open up. There and there. Where does the OH go? If I put the OH group here, the problem with this is that carbon's got 3 choices. It could form the double bond here, it could form the double bond there, or it could form the double bond there, which is where I need it to be. 3 choices, and the preferred choice is not what I want. I need to make sure that double bond is out there between the CH2 group and the ring. So that means I'm going to have to put the OH group on the CH2 piece. If I do this, this OH group is going to be eliminated. Whoop! Off it goes. That carbon is going to form a double bond. No shift's going to happen. It prevents it. And the only choice that it has is forming the double bond right there, which is where I want it to go. So here's a review. Tons of reactions. Tons of reactions in alcohols. But we've talked about alcohols undergoing substitution. So I add HBr, HCl, HI, PBr3, PCl3, SOCl2. And notice that the phosphorus tribromides, trihalides, thionyl chlorides, they're really only for primary and secondaries. Tertiaries cause a problem. Too bulky. Too bulky for that SN2 reaction to take place. That's why they don't rearrange. SN2's happening. We also talked about these alcohols that can be converted to a sulfonate ester by using things like tosyl chloride. And that will eventually go and give you a substitution reaction. A good leaving group goes on. And now we finished up elimination. 2 major forms, heat and acid, or a phosphorus oxychloride in pyridine. And here, tertiaries are great. Tertiaries work the best as far as elimination goes. So folks, there's quite a bit. I know. This is just going to keep adding. It's a lot of material. I hate that we start off the semester like this, but this is how it normally goes. We just swamp you with reaction after reaction, mechanism after mechanism, and then we just see if you sink or swim. I hope that that's not the case. And if you are feeling that, that is very normal at this point. But at no means at all are we yet finished with the alcohol reactions? This is just the beginning. That's all that this is. It's just the beginning. So bear with us. We'll make it through the alcohols. I promise this is kind of the worst chapter out of the bunch. The others are not going to be quite like this. They might get tricky. There might be a lot of information. But this one seems like it's very burdensome. And it could just be a new class at the beginning of the semester and you're just trying to adjust to everything. And maybe that's the case. But folks, we're only 4 sections into the chapter. 4 sections out of many. That gives you an idea of where we're headed. So don't freak out on me. This is where this kind of module is going to stop as far as part 1. And good luck on the online assignment that will follow with the elimination and the substitution of alcohols.